All right, thanks to the organizers for inviting me and giving me the opportunity to give a talk here. So I'm going to be reporting on some progress I've had recently with Bertrand Gunnin on Seymour's F-Flow conjecture from 1977. So this conjecture sits at the heart of polyhedral combinatorics, and it's interesting for a variety of reasons, and you can state it in many different ways. So I'm going to state it in a language that you're most comfortable with, affine binary spaces. So you give me an integer n greater than or equal to 1 and a subset of the 0, 1 hypercube, n-dimensional. I'm going to say that the set S is an affine binary space if whenever you give me 3 points in S, their sum modulo 2 is also in S. Okay, so that's going to imply that whenever you give me an odd number of points in S, their sum modulo 2 is also in there. Whenever there's some sort of duality going on with affine binary spaces, if you give me an affine binary space S, I can define this new set of points Y so that Y transpose X intersects, Y transpose X is 1 modulo 2 for every point in S. If you look at this set of points, this gives you another affine binary space. So I'll be referring to this set of points, let's call it R. I'll be referring to that as the blocker of S. And Lehman showed in the 60s that this is an involution. That if R is the blocker of S, then S is the blocker of R. So this notion of duality will be very important for our talk. Is it clear how I'm defining affine binary spaces and blockers? Okay, good. There's another way to define affine binary spaces, and you might be more comfortable with that, and that is in terms of signed binary matroids. So we're given a binary matroid M over ground set E, and we're given a subset of the elements. Let's call those elements sigma. I'm going to look at the pair M sigma. I'll refer to this as a signed binary matroid. Essentially, we think of the elements in sigma as odd elements, and everything else as even elements. So that's where the term signed comes from. I'll say that a cycle of the original matroid M is odd in M sigma if it contains an odd number of elements in sigma. Now, there's this operation that preserves the parity of cycles, and it's called resigning. Essentially, whenever you give me a cocycle D, what you can do is you can replace sigma by sigma symmetric difference D. And that will preserve the parity of every cycle. Essentially because cycles and cocycles have an even number of elements in common. So the odd cycles in M sigma are the same as the odd cycles in M comma sigma symmetric difference D. So this is also going to be crucial for us. Now, if you give me the odd cycles of a signed binary matroid, it will always give me an affine binary space. Essentially, whenever you give me 3 odd cycles, their symmetric difference is going to be another odd cycle. And not only that, every affine binary space is constructed in this manner. So whenever you give me an affine binary space, you can actually represent it as the odd cycles of a signed binary matroid. So this is the second way to think of affine binary spaces. Okay, so we're going to need the notion of minors for signed binary matroids. It's an extension of minors for matroids in general, but you need to respect the parities of the elements. So let's say you're given a signed binary matroid. You could think of M as the cycle matroid of this graph, and these wiggly edges are the odd edges, are the elements in sigma. Okay, so the first operation is deletion. You can give me any element, I can delete it. And what that means is you just delete that element from both your matroid and also from the set sigma. All right, so here I deleted that diagonal edge. over here. Another operation is resigning. You can take any cocycle, or cut in this case, and it can resign along that cocycle. So here, I took this cocycle, and I replaced this odd element by these two odd guys. So that's called resigning. And then the third operation is contraction, but you cannot contract every element. You can only contract elements outside the set sigma, or you can only contract even elements. So, and that just corresponds to contracting the element in the matroid M, and then sigma remains unchanged. So here I contracted this guy, and I got this guy. So if you would like to contract an odd element, first you have to resign and make it even, if you can, and then you contract it. All right, so this the notion of minor operation respects the parity of the elements and also respects the odd cycles. All right, so with this now, we're ready to dive into, so a minor is what's obtained out the sequence of these operations, of course. Okay, so now I can get to the main topic of the talk. So I'm going to say that a sign matroid M sigma is ideal if the corresponding set covering polyhedron is integral. What is this polyhedron that I'm looking at? So I'm going to assign variables to the elements of my matroid. And for every odd cycle, I'm going to have a corresponding constraint. Essentially, I want the sum of the variables along that odd cycle to be at least 1. So I'm trying to fractionally cover the odd cycles of my signed binary matroid. And I want that polyhedron to be integral. So I want the extreme points to all be integer. And so the key observation is what Paul Seymour made in 1977, which is that if M comma sigma is ideal, then so is every minor of M sigma. Essentially, minor operations in terms of this polyhedron correspond to restrictions and projections. And because those operations preserve integrality, the notion of idealness is closed under minor operations. And so the natural question comes about, what are the excluded minors for this minor closed class of signed binary matroids? So it turns out that being ideal is closed under taking blockers. So the very first notion I defined at the beginning. So Lehman and Fulkerson proved that if you give me blockers M sigma and N gamma, then M comma sigma is ideal if and only if N comma gamma is ideal. Essentially, it corresponds to the theory of blocking polyhedra. And that preserves integrality. So here you're going to preserve, idealness is closed under taking blockers. And I should point out that this is not the same thing as duality in terms of matroids. Okay? And so in particular, what this implies is that the excluded minors defining the class of ideal signed binary matroids is also closed under taking blockers. So if you give me one excluded minor, its blocker will be another excluded minor. Okay, so Seymour conjectured in 1977 that there are only 3 excluded minors defining ideal signed binary matroid. So what are these excluded minors? The first one comes from the Fano matroid. I like this representation of the Fano matroid. This is a graphed representation, so you have K4, and then you have a T set, and then your matroid is the cycles of the underlying graph plus the T-joins. And so your underlying matroid is the Fano matroid, and your signing is all the elements. Every element is odd. So the red edges that you see here, including the T-set, are all odd. And this turns out to be equal to its blocker. So that just stands on its own. The next excluded minor comes from graphs. You take K5, and then you sign every edge odd. That's another excluded minor. And the third one is the blocker of this guy. And the blocker of that is R10 with this signing, essentially. So these 3 edges are odd. Everything else, including the T set, is even. And that's the conjecture. Any questions so far? Okay, so this conjecture, again, as I mentioned at the beginning, is very important in many different, in different areas, including combinatorial optimization. One reason for its importance was basically weakly bipartite graphs. If you've heard of those, essentially, there was a conjecture there, again, made by Paul Seymour, that was only concerned with ideal sign binary matroids where the underlying matroid was graphic. And if you look at it, the only excluded minor where the underlying matroid is graphic is this one, this beast over here. So you could try to, just as a first step, prove the conjecture for the case where M is graphic. And this is what Bertrand did in the late 90s and early 2000s. What he showed was that K5, or odd K5, is the only excluded minor where the underlying matroid is graphic. And this was a very nice result because it gave a complete co-MP characterization of weakly bipartite graphs. If you've come across those, you know what it's about. And his proof relied on this very powerful tool given by Alfred Lehman in 1990 on minimally non-ideal clutters, which was just and his result is a very nice co-NP characterization of set covering polyhedra that are integral. So what do we do? So we essentially have two results. The first one is a result in support of the conjecture. So what it says is that, let's say you give me a blocking pair of excluded minors, M, sigma, and gamma, different from the ones that are already known. Okay? So the conjecture is there isn't none. There isn't any. Then what we can do is through every element of the underlying matroids, which are the elements are the same, what we can do is either in the sign binary matroid or in its blocker, what we can find is a minor that looks a lot like the first excluded minor. Essentially, you have the phono, and every element is odd except for one. So here you could just pick the element to be the T set. So what we do is, whenever you give me, again, to repeat the result, if you give me a blocking pair of excluded minors different from the three ones you already know, through every element in one of the two, you can find this minor. And to prove the conjecture, all you need to do is turn the parity of that last edge, turn it from even to odd. And then you'll be done. And how do we prove this? The proof relies on Lehman's theorem, again, the theorem Bertrand already used in the early 2000s, and another result. And what is the other result? The other result is actually an exact result. What it says is that the only excluded minors that have an odd triangle are the first two ones. If you look at the third excluded minor, it has no triangle or circuit on three elements. And so what we show is that the only excluded minors with an odd triangle are essentially these two. And this, together with Lehman's theorem, gives you the first result. So for the rest of the talk, what I want to do is I want to sketch the proof of this result. It combines a lot of nice tools that are in the literature, and also a recent tool that Caroline and James proved for us. So I'm just going to go over the proof of that. All right, so what we want to show is that the only excluded minors with an odd triangle are these two beasts. So suppose that's not the case, and let's pick another excluded minor that has an odd triangle. Then this Lehman's theorem, we're just going to use it as a black box. What it proves is that there is a resigning where every element is odd. So we're going to pick that signing. So you don't need to worry about parity anymore for now. Every element is odd. It also shows that M is a simple matroid, and that every element of the matroid appears in exactly 3 triangles, which have to be odd because every element is odd. All right, so the first step of, what I said was every element was in exactly 3 triangles. So let me pick an element. So this is going to be fixed for now. I'll pick the element E, and I'll pick the 3 triangles that go through it. If the 3 triangles don't look graphic, then essentially what you have is the first one, which is the one I've already excluded. So I may assume it looks like this. What I'm going to do is I'm going to contract the element E. I'll get this. And then the fact that M was simple and every element was in 3 triangles tells you that aside from these 3 parallel classes, everything else is simple. So what I'll do is I'll just keep one edge from every class, and then I'll get the simplification. I'll refer to F, G, and H as lambda of E. So for every element E, I can associate with it a set of 3 elements that I'll call lambda of E. And the first step of the proof, and the hardest part, is proving that there is no circuit in the simplification of the contracted matroid that contains F, G, and H. So let me tell you why that's the case. So imagine that you had a circuit going through F, G, and H. So it's F, G, H plus this T set that I have here. That's going to give me the circuit. Then what I can do is I can uncontract the element E, and what I'll end up with is this guy. And this is just S8. So M has an S8 minor. And so the most involved part of the proof is saying that we can switch the parity of this circuit that I have here if necessary. And with that, you put those 2 together and you get that MEM has an F7 E, F7 minor, because S8 essentially has an F7 minor. And if you know that this circuit can have either parities, then you put it together and you get an F7 E, F7 minor. Okay? So we may assume that the simplification of M contract E has no circuit containing FGH. Now let's think about this. We have 3 elements in our binary matroid, and there's no circuit going through them. Why is that? So one simple reason why that happens is that the 3 elements that you have form a cocycle. If they form a cocycle, you cannot have a circuit going through them because cycles and cocycles intersect in an even number of elements. And so that's a step 2. What we show is that lambda of E cannot be a cocycle. What's another reason why F, G, and H do not appear in a circuit? Essentially, they could be in different components of your underlying matroid. So there could be a connectivity fault. And so Gerard, Cornijols, and Bastrangona in 2002 proved that M is actually internally 4 connected using Lehmann's theorem. But it's not M that we care about. It's M contract E simplified. And Caroline and James proved that you can always find 4 elements, E1, E2, E3, E4, so that after you contract either of those and simplify it, you still remain internally 4 connected. And this is true for internally 4 connected matroids where every element is in exactly 3 triangles. So they proved this nice result. And so you put those 2 together and you get that, well, you don't really have a connectivity fault. So what's going on? I have no connectivity fault. My 3 elements don't form a cocycle, yet I have no circuit going through them. What's another simple reason why there is no circuit going through F, G, and H? What is it? So that was the first one. They form a co-circuit. Think of graphs. If I tell you 3 edges, what's a sufficient condition for 3 edges never to appear in a circuit? They're incident to the same vertex. They could be incident to the same vertex. And this is a magical result that Paul Seymour proved in 1986, that if there is no connectivity fault and they don't form a co-cycle, that must be what's going on. The simplified matroid obtained after contracting I must be the cycle matroid of a graph where F, G, and H are incident to the same vertex. So we have this happening for every EI. And we have 4 of those. Essentially what it says is the original matroid is very close to being graphic. And so what we show is that actually M is just a deletion away from being graphic. And this uses ideas on even cycle matrix, graphic even cycle matrix. So it uses ideas from Xi from 1982 and Bertrand's and Irena's and Paul's result from 2013. It's motivated by their result. And well, Bertrand's result tells you that M is not graphic either. If it was graphic, I'd be done. So you put these two together and it basically tells you that the matroid M must have a K4 restriction. It's just, this one's easy. And then a very subtle counting argument using Lemma's theorem tells you that if you have a K4 restriction, then you must be one of the 2 excluded minors. And that's the proof. So what we showed was that the only excluded minors with an odd triangle are these 2 beasts. And I'm just going to end with the flow and conjecture. That's still open. Thank you.
All right, are there any questions?
Yes.
Can you say a bit more about the results of Lemma's that you used?
So Lemma's theorem essentially says it's actually about 0-1 matrices. It's not just about affine binary spaces. If you give me a 0-1 matrix or a clutter, if you will, essentially you could look at the minimal rows. So if you give me a clutter for which the set covering polyhedron is not integral, but whenever you move to a proper minor, the set covering polyhedron is integral, then what you can say is that you're either in a degenerate class, and actually it's and those are degenerate projective planes. Those guys are not binary. Or there is a very good reason why your clutter is non-ideal. It's because there is a row submatrix, a square row submatrix, where if you collect the minimum cardinality rows, it forms a square non-singular row submatrix. And that is already enough to guarantee why your clutter is non-ideal. Because if every row has cardinality R, I could just assign the point 1 over R everywhere.
So that's the core of the clutter.
That's the core of the clutter if you're not a degenerate projective plane. And not only that, it says that you could do the same in terms of the blocker. And if you put these 2 matrices together, there's very nice matrix equation they satisfy. And so that's the result, essentially.